All right, we're going to go through some basic definitions of things. I'm going to start with position, time, and displacement. Hopefully we'll get through all of those. So let's start out with this example of the pumpkin dropping off the house, which we talked about before. And we initially say that using the particle model, the pumpkin starts up here, right? This is its position. And then we drop it, and it moves down there. And then we had down there, and then finally it ends up down here, right? Well, what we can do is we can create what's called a position vector, okay? So if we want to draw things on a graph, which usually we do because it makes it easier to measure things, we can say that this is x and this is y. And we know that the origin here is 0, 0, so this is our origin. And when we're drawing a position vector, we start at the origin and we go to the initial position. So the initial position here, I'm going to call R0, okay? And we're going to say that this goes up to here, and this is a vector called R0. So this is the position, and this is the position vector. Okay, so this is a vector, and this is just a position. Okay. Now, if this is our second position here, and the third, and the last position, we can create vectors for each of these. So I'm going to use different colors just to kind of illustrate what I'm doing here. So this vector is called R1, and the little arrow above it represents that it's a vector. This vector is R2. And finally we have R3. Okay, so the fact that it's a vector is indicated by the fact that there's a little arrow over it. So what is a vector? Well, if you watched Despicable Me, then you know that a vector is something that has a magnitude and a direction. So the magnitude in this case is given by the length of this arrow. So if we're looking at R3, this length here, which we will call the magnitude, or the absolute value, same thing, that's our magnitude. The direction is indicated by the angle, so we'll call that theta. So we can say that R3 has a magnitude that is given by the absolute value or the length of the vector, and the direction is given by theta. Okay? So, we can kind of break this up a little bit into positive or negative. So, one thing is that positive direction is indicative of direction also, as is negative. So what does that mean? Well, if we're looking on just an x scale, so this is 0, 1, 2, say x over here, this is -1, this is -2. The positive or the negative indicates the direction away from 0. So if we have +2, this is positive here, and over here we've got this one, which is negative. This means it's left of 0, and this one means it's right of 0. Okay, so that we can use positive and negative to indicate the direction as well as an angle. Okay, now let's talk about displacement. Right? if we initially, so this is, we're going to say that this is our origin again, and we go here, R0, and this is our R0 vector, and we want to go to R1. R1 is over here, so this vector is called R1 arrow. Then we have a difference between these two, going from our initial point to our second point, okay? This we denote by delta R, so that's kind of like the change in position, because remember delta means change in and R means position. This is called a displacement vector. When our position changes, it has a displacement. So the change from R0 to R1 has a displacement vector of delta R. And mathematically, the way we can write this is that the final position of R is going to be equal to the initial position plus delta R. Now in this case, our final position was R1, but that's still going to be equal to the initial position plus the displacement vector, okay? The other way we can write this is if we can subtract the initial position from both sides, then that means the change in position has to be equal to our final position minus our initial position, which is kind of what we expect with a delta. Now with vectors, we can add them, okay? And this is kind of what we're doing in this case. So to add a vector, we take the tip of the first vector and add it to the tail of a second. So if I have a vector A, we take the tip of A and add it to the tail of B. So this is vector B. Okay. So that's the first step, is add tip to tail. So we're going to go here, this is A, then we're going to start with the tail of B right at the tip of A and go down like this, right? Now, if we're adding these, so we want to find out what A plus B is, we go from the very beginning point, which is here, to the very end point, which is here. So if we call this vector C, then we've added A and B, and that equals C. So C starts at the very beginning and goes to the very end, all right? So this is how you add it. If you're going to subtract a vector, then what you're going to do is you're going to flip the vector that's negative. So if we want to say A minus B, well, this one has the minus in front of it, so we're going to flip B by 180 degrees. So if B is equal to this, then minus B goes this way, right? So to calculate what A minus B is, we're going to take A, which was the same thing we had before, and on the tip of A, we're going to add minus B. And minus B, remember, goes up this way, which means our C, in this case, is going to be going this way. Okay, so subtracting just means flip the vector around 180 degrees, okay? So what does this have to do with our displacement vectors? Let's think about it this way. When we are going from our initial position, R0, to our final position, R1, then we are basically adding our delta R here. So remember, R0 plus delta R is going to be equal to R1. So this is a way to use vectors to find a final position from an initial position. Hopefully that all makes sense. Now, one thing I want to note is time. Time is not a vector. It doesn't have a direction, even though we think about moving backwards in time. Realistically, we can't. So we just basically have something called a scalar here. Scalar because it has no direction. Now, that isn't to say it's not useful. We use lots of scalar values that are useful. Temperature is another good example. But we want to keep in mind that when we're working with time, we're a lot of times going to be dealing with a time interval. So this is going to be our elapsed time, or our time interval. And the fact that there's a delta in front of us should tell us that we want to take a final time minus an initial time. Okay? And the reason this is important is because, we've been talking about changing position with time, and we're talking about time intervals. So now we're going to try to look at it in terms of our particle model and our displacement vectors. So rather than drawing pictures of little movies and just particles moving around, we're going to try to add vectors to it to help us better understand how things move.